Welcome to the World Stem Cell Summit session on Organoid Revolution. My name is Amritha Jaishankar. I'm with the Maryland Stem Cell Research Program, and I will be chairing this session today. So our speakers today are Dr. Colin Bishop, Dr. Thomas Shupe, and Dr. Paolo Di Capi, who will be discussing this technology today. So the goals of our session today are to give you an introduction to this widely popular technology and to enhance your understanding of three-dimensional culture systems and to create an appreciation for complex organoid integrated studies that our panelists will be discussing today. So, everywhere you see organoids have been in the news lately, it seems like. So what you see on the corners of the slide are what they actually look like, and what's in the center is what some people think they look like or what we'd hope they would be. But no matter what, you can see that over the last few years, there has been a really increase in the number of publications. So it's really skyrocketed over the last few years. There's about a 12-fold increase in the publications in this space. And this is interesting because the concept of organoids as such is not really new. And our need to understand morphogenesis has existed for several decades. But it's interesting because the ability to reprogram human somatic cells into induced pluripotent stem cells and then move them into other specific cell fates has really revolutionized the way we study development and disease today. And in a way, all the progress that we made in understanding this development and in developing these in vitro protocols have sort of culminated in this organoid technology as we know it today. And so I'm just going to give you a very brief introduction to what organoids are. So an organoid simply means resembling an organ. Most traditional cell culture systems are two-dimensional and planar and static, as opposed to the organoids, which are a three-dimensional culture system, in vitro culture system, in which stem cells organize themselves to recapitulate, at least in part, the development of the organ, the architecture, functionality, and genetic signature of the original tissue. So organoids can be derived both from pluripotent stem cells as well as from organ-specific adult stem cells. And so the point that I would like to make is, the path that you take is a little bit different. So if you're starting from a pluripotent stem cell, you take them through a series of developmental steps to get to that particular organ. If it's an adult stem cell, it's already tissue specified. You recreate the niche to get to that particular organ. But no matter which way you go, the fact is that we've now been able to make organoids from organs of all three different germ layers. And therefore, this really illustrates the power of this technology and how broadly applicable it is, and that perhaps that we could have all major organs in a dish someday. Here's an example of a cortical organoid. So it's a specific brain region organoid. What you can see that in addition to being able to develop the relevant cell types, it also really recapitulates the architecture of the fetal brain. And this is the work from one of the companies that we help support in Maryland, moving university technology into a company studying these. And so as you can see, there can be numerous applications for these stem cell-derived organoids, whether it's in biobanking, whether it's in disease modeling, drug testing, drug discovery, or simply understanding the mechanisms between disease and healthy tissue. But let's talk for a second about drug testing. So drug discovery is a lengthy process that's associated with a tremendous cost and a high failure rate. And the reason most drugs fail is because we don't have the ability to effectively validate the safety and efficacy of these drugs. And that's primarily because we lack the appropriate model system, because current 2D culture systems and animal models really fail to predict human responses and don't accurately mimic the human pathophysiology. So there's really an unmet need to develop these in vitro model systems to accelerate drug development and personalized medicine. And so organoids are one step in that direction. But the next step needs to be able to integrate multiple tissues because our cells and our tissues don't exist in isolation in our body. And so People have developed organ-on-a-chip systems which combine advanced microfluidic technologies and tissue engineering approaches to simulate the biology and physiology of human organs. And you'll be hearing about this today. And furthermore, the next frontier in this is to then combine several of these organs on a chip to mimic the interconnectedness of these organs to develop a human on a chip so that you can really revolutionize personalized medicine and drug development. And in a way, you can imagine how if you can recreate all the organs from one particular genetic makeup, you're essentially having yourself on a chip to be able to move these personalized therapies forward. And so with that rapid introduction, I will invite our first speaker, Dr. Colin Bishop, who's a professor at Wake Forest Institute for Regenerative Medicine. Thank you.
Thank you very much, Amritha, for the introduction, and thank you to the organizers for inviting me and letting us talk about some of the things we're doing in Wake Forest. As Tom Shupe has previously mentioned, we have a large effort into building a body on a chip, which is called the ECHO program. I'm, in this presentation, going to talk about making the individual organoids, not all of them because there's just not time, but the main organoids that we are using for the body on the chip. And then Tom Shupe will tell you how we're integrating these organoids into a single, almost human on a chip. The XCEL program is a large program involving different universities such as ECBC, Johns Hopkins, Georgia Tech, University of California, and WFIRM, which is the lead institute. What we want, of course, are integrated human organoid constructs that function as a system. They're going to be supported on a platform, and they're going to model the effects of drug, toxic agents, and also diseases. Our first organoid that we made was, of course, the liver organoid. And the way we made this is that we took the main components of a liver, which are hepatocytes, the inflammatory Kupffer cells, hepatic stem cells, stellate cells, and liver sinusoidal endothelial cells, and we mixed them in the proportions that you can see at the bottom there. These are all bought commercially from reputable suppliers. And this is how we form them, and there's a little film in the bottom left if you could make it work. So we initially used 96 well plates. There it goes. This is our automation. But anyway, we initially started using 96 well plates. We mixed the cells. We put them into this machine, which dispenses them into the wells. And we left them for 4 days, and they compact, and they form these spherical organoids, presumably spherical because it's the most stable state of least energy. We then moved it up to 384 well plates, and we actually even have it even higher now. But again, there's another little film at the top right. This is them forming. This is looking at a single organoid forming through an IncuSight system, which is essentially a real-time microscope. And at the very bottom, you can see live dead staining of these organoids over 28 days. That's 1 month. Live, of course, is green, and dead is red. Looking at them, this is like the basic immunohistochemistry on 2-week liver organoids. We can see that they're compact. They don't show a fibrotic center or anything, or a necrotic center. They are approximately 200 to 250 20 microns across. We want to keep them small like that so that we can get plenty of diffusion of nutrients in and out. We found that when we got them up to about 1 millimeter, we always, after a couple of weeks, we always found necrosis in the center. You can see the E-cadherin staining for tight junctions, connexin 32. PAS staining shows that they have glycogen storage, keratin 18 and CE68 staining all look what you'd expect and look they show that the organoids are in a good condition. We also did TEM on the organoids, and we can see rudimentary biocaniculae and these, oh God, excuse me, I can't see as well as I used to. Okay. And we can see these adjacent to the hepatocytes, indicating that we're going to get the establishment of a primitive biliary system. We can also see in the bottom two stainings, these are whole mount stainings where we just fix the organoids and stain them. We can see P450 reductase and albumin, and the yellow color indicates that they're simultaneous there. We can also see vimentin, which indicates the stellate cells, and albumin, of course. And you can see the stellate cells are long and spindly and are getting in between the hepatocytes there. When we look at functionality over 1 month, we can see that these 4 graphs are showing ATP content, or top left. What's the next one? Urea, alpha-1 antitrypsin, and albumin. I'm sorry, I just can't read which is which. And which shows a good functionality for those 4 markers of functionality over a month. We actually have taken them further, and they can go out to 6 weeks, but we stop at a month. We can also see here the difference. This is SIP analysis, and we can see the difference. You can see the difference between 2D and our 3-dimensional organoids when we challenge them with CYP, with SIP analysis. The metabolites, of course, are measured by mass spec. And you can see for either of those 3 assays, you can see that after about 7 days, the 2D hepatocyte organoids are pretty well finished, whereas the 3D organoids are doing a lot better and are remaining quite functional. We have been looking at these organoids to see if we can produce disease states. And one drug that we looked at, which was a withdrawn drug that people have been talking about, troglitazone. And when we can get a great dose-response curve with troglitazone with the EC50, about a little less than 100 micromolar. And we can see when we treat the organoids and then stain them, you can see that there's an accumulation of neutral lipids. That's the green stain at the top, which is acting as a model for steatosis. And you can see in the red, the intracellular accumulation of phospholipids models phospholipidosis. We also have been working on a model of fibrosis with the liver organoids, and we treat them with LPS, which induces fibrosis. These are a series of top secret molecules that we have developed which we hope will play a role in reducing fibrosis. And you can see from the pictures compared to the DMSO control with the, with the collagen 1 is in green, you can see that most of these molecules are actually reducing the amount of collagen after treating them, the fibrotic organoids. We also have been making cardiac organoids. Here we're using cardiomyocytes, which are derived from iPS lines. We're using 70% iPS-derived cardiomyocytes, 25% fibroblasts, 5% endothelial cells. These are the characteristics of the cardiomyocytes that we get. These are from axiogenesis, and you can see there are all 3 types of cells there, especially the nodal cells, the atrial cells, and so on, and the ventricular cells. Again, these are pictures of our organoids. We make them in exactly the same way, only these remain beating, so they initiate beating after a couple of days. But we have had these organoids beating now for well over 6 months until they got infected, unfortunately. But they have a very, very long beating lifespan. And on the right, you can see the VEGF expression from the endothelial cells, which are mixed in there. Again, this is a whole mount picture. There is a little picture on the left, which should start beating in a minute. What you're seeing, I hope you'll see, is a beating cardiac organoid, and what we did was take like an iPhone camera underneath, and one of our grad students wrote a program which turned the beating to somehow digitized it and produced it at the bottom right, the peaks that you see. Guess we're not going to see the organoid beating, but it's quite impressive. Again, we looked at the properties of these cardiac organoids. You can see the baseline beating, the beating after we added isoprotenolol, and quinidine, which is an anti-arrhythmic drug. We also simulated a heart attack, if you like, by taking the oxygen rapidly out of the medium using a 2-enzyme system rather than put it in a hypoxic chamber, which is too slow. And you can see very quickly that the no oxygen start having extremely aberrant beating until it eventually stops. We're using this model as a drug screening model to see if we can find drugs which can quickly intervene in these situations. Again, this is cardiac toxicity with 4 cardiotoxic drugs, showing that there's a good dose-response curves on the left, and on the right, we are looking at apoptosis. So we can see that the 4 drugs on the left are all toxic, but they're not all toxic due to apoptosis, as you can see on the right, indicating there are the different mechanisms that these drugs work by are actually reflected by our apoptosis assay. Another of our grad students is creating a brain organoid. We are not so much concerned here with making an exact brain with all the parts to it. What we want to look at is the blood-brain barrier. So we want to see what sort of agents will disrupt the blood-brain barrier. There's been some suggestion inflammation in early development could disrupt the blood-brain barrier, leading to autism. So we want some sort of model. Again, it's exactly the same. we're having astrocytes, microglia, oligodendrocytes, and neurons, which are iPS-derived, and the microvascular endothelial cells and pericytes are primary cells. Again, these are just a simple characterization of the organoids, showing that they have tight junctions and so on and so on. This is the killer cell picture, if you like, showing that there are very good tight junctions around the edge of these spherical organoids. And we used FITC labeled IgG to check the permeability. So on the left, you can see a control. And when you add histamine, which is known to disrupt the blood-brain barrier, you can see that the IgG will penetrate, but only if the blood-brain barrier is actually breached. Finally, I want to talk about another organoid, which I think we're probably about the only ones in the world that have, and this is a human testicular organoids. And I work together with my colleague, Dr. Sadri, to establish these. Essentially, what we have done is taken biopsies of human testes. We've isolated Sertoli cell, Leydig cell, and also we have spermatogonial stem cell cultures which can remain functional for more than 6 months. What we have done here, exactly the same way as we've made our other organoids, we've put them into 96-well plates. You can see at the top, we've just labeled a few of these cells with calcine, I think, and they eventually form a nice organoid. And these are the plates that we're using right now. They're 96-well U-bottom plates. Cells go in, they fall down. After 2 or 3 days, they form very tight organoids. This is H&E showing it's a compact looking testes organoid. Here we labeled the 3 cell types that we put into the organoid because the reason we did this is with all of our organoids, the liver, the blood-brain barrier, all of the organoids that we've made, we've noticed that there's quite a lot of self-organization in that cells seem to go where you think they would go. It was mentioned earlier, in another lecture, that when you take tiny little carrots of skin but put them back in the skin in any orientation, they seem to reorientate themselves. But anyway, these organoids tend to self-organize. So what we did in this case was we labeled the spermatogonial stem cells in blue, the Sertoli cells in yellow, and the Leydig cells in red. And this is just a confocal image, and you can see on the surface it's sort of fairly mixed up, but not so much blue. But when you take a middle section, you can see most of the spermatogonial stem cells are in the middle with the Sertoli and Leydig cells on the outside. Of course, we were looking to see if we could detect spermatogenesis in these organoids. I guess that was always one of the things we wanted to see. And in fact, we can. After we have formed these organoids, we make a differentiation media, and we then let them differentiate for 23 days. And this is a DNA fish which is detecting about 10, maybe 15% haploid cells. You probably see it better than me, but you can see X and Y bearing sperm in there. The testes organoids are also interesting from the point of view of drug screening, but there is a lot of fears about environmental toxins leading to infertility. A lot of workers in Mexico and India, for instance, that spray different types of insecticides with very little protection. It's been shown, it's been feared for a long time that their fertility rates are dropping. So we want to use our organoids, our testes organoids, of course, to screen not only for drugs, so it could have an effect on fertility, but also for environmental factors. And this is testing 1, 2, 3, 4 drugs that we actually use in the clinic and we know have an effect on the testes. And they can see that they show pretty good dose-response curves. And they also, their IC50 values, although not completely in line with what you would expect in patients, are certainly showing toxicity. And that was why I asked a question a bit earlier about how you relate the actual toxicity in a patient to the toxicity you would see in an organoid. And I think, the main answer is you've got to do a lot of it and look at these things very carefully. This is just caspase 3,7 apoptosis after drugs, after giving drugs, which just confirms the toxicity. One thing that we've been trying to do quite a lot is cryopreservation of these organoids, because it's fine if we can make thousands of these organoids in 96 or 384 or whatever plates in our lab or anywhere. Unless we want to do the testing ourselves, how is anybody else going to use them? And so we have played around with different ways of cryopreserving these organoids, from standard cryopreservation methods to vitrification, which is a very fast freezing within seconds. And we actually found that vitrification of the testes organoids worked very well. We could keep them frozen for a couple of weeks, then bring them back, and after 1 or 2 days, they again resume full functionality. And right now, in fact, we are collaborating with a group in Hawaii who are working on Zika virus. And they contacted us and said they would like to see how Zika virus infected the testes. And so rather than them having to work up how to make all these things and grow the cells and grow the spermatogonial stem cells, we just made a few thousand of these, frozen them down in small batches of about 100 by vitrification, and put them in FedEx and sent them to Hawaii. And it works, and it works real well. We're having more trouble with the liver. It seems to be more sensitive, but that's one of our goals, so that when we do make these organoids, we can ship them around to different people, and different people can play with them as they want, test their own drugs and so on. Finally, the final slide, I guess the portfolio we have now is the liver I've spoken about, the cardiac, the lung I haven't spoken about, but that's in hand, and the vascular. We have the testes, we have GI, blood-brain barrier, and we are working on just about all of these, including using tumor organoids for testing different drugs that might be of use in personalized medicine. And I will now turn it over to the next speaker.
So our next speaker is Dr. Thomas Shupe, Assistant Professor and Scientific Coordinator of the XCEL program at Wake Forest Institute for Regenerative Medicine.
Thank you, Amritha. So I'm going to talk, Colin described the characterization of a lot of these organoids. I'm going to talk about some of the experiments that we've done with them. And I've divided it into two sections. The first section is going to be toxicology and pharmacology on individual organoid cultures. The second half is going to be integrated organoid systems, where we're doing studies with multiple organoid types under a common media. So here's an example of some of the types of experiments that we've been doing. And this is a vascular organoid construct. Colin didn't describe this one, but briefly what we do is we use a semi-porous silica membrane and culture primary endothelial cells on the top surface, and we can position tissue organoids below the surface of that membrane. And what this does is it represents sort of the capillary bed, where compounds that are in the circulation have to cross the endothelial layer or the capillary in order to penetrate into the tissue. And we can these vascular constructs are easy to set up, so you can have an entire circulatory system that's partitioned from all the individual organ compartments by an endothelium. So in this first experiment here, this is histamine treatment. We show that in the intact monolayer, and we're using transendothelial electrical resistance in order to monitor this. When we add the histamine, we get a drop in resistance across the endothelial monolayer, and when we wash the histamine back out, those tight junctions are reformed. You reestablish the barrier functionality of the vascular organoid, and the resistance across that endothelium comes back up. We also did experiments with these with fluorescent dyes, where we partitioned a fluorescent dye in the lower chamber below the vasculature, added histamine, and you can see that dye coming out. So here we can see in the tall bars there on the left, when you don't have confluent vasculature, the dye immediately begins to leak out and you lose dye over time. The darker bars represent the tissue organoid, or the vascular organoid with a confluent monolayer, and you can see that the dye is retained fairly well inside the tissue microreactor until you add the histamine. That opens up those tight junctions, and then you see the fluorescent dye starting to come out from between the endothelial cells. More toxicity in single organoids. Here's some data from our liver organoids. This is acetaminophen intoxication. On the left, you can see albumin. That's albumin production. You can see that at 0 and 1 micromolar, you get good albumin production. At 10 micromolar, you lose albumin production as the cells die. 10 micromolar or 10 millimolar is 10 millimolar is equivalent to a human serum concentration that would be considered toxic. For urea production, you see the same thing. At 0 and 1, the urea production is higher. When you get to 10, it drops as the cells are dying. We did another experiment similar to this, but we used the clinical countermeasure to acetaminophen intoxication, N-acetyl-cysteine, to see if we could actually rescue the system with a relevant treatment. So these experiments are a little different. Rather than looking at a product of the cell to determine health, we're looking at molecules that are supposed to be inside the cell but are released when the cell dies and opens up. LDH, lactate dehydrogenase on the left, and alpha GST, which is a phase 2 detoxification enzyme on the right. So here we can see in our control, the lactate dehydrogenase remains inside the cell. The dotted line there is the one that spikes up is the acetaminophen, where we add our acetaminophen, we get a burst of release of LDH, and then it comes back down. When we do it with N-acetyl-cysteine, which is a glutathione precursor and protects the cell from the toxic effects of the acetaminophen, you don't get that burst release of lactate dehydrogenase. Similarly with alpha GST, the two bottom lines, the solid lines of control, The tight dots down low are when we add the acetaminophen with N-acetyl-cysteine, which protects, and that top line where you're losing all the GST is where there's no countermeasure, and it's just acetaminophen intoxication. Let me go back. Here's some metabolite analysis that we did. Basically, Johns Hopkins did this for us. You can see the far left in the big circle. This is just a profile of what's in the media. That's the control media at an early time point. You can see those gray dots over to the right on the big circle. Over time, they condition the media to contain the plasma proteins that you'd expect liver organoids to be producing. When you intoxicate with acetaminophen, you get this cluster up in the upper right-hand corner. This is just saying that the contents of the media has changed drastically. And when you co-administer N-acetylcysteine to rescue the cells, you bring that profile back into alignment with the normal controls. Colin talked about this a little bit. Here's some examples of FDA-recalled drugs that we tested with the liver tissue organoids. Triglydzone, you can see viability there at the bottom. As you increase dose of triglydzone, you get a commensurate loss of cell viability. And there's the phospholipidosis that Colin described in the red panel up top. Estemazole, another FDA withdrawn drug, and this was a drug that showed some cardiac problems. And you can see in the far right, we do lose at higher concentrations. We lose viability when we add estemazole to the cardiac organoids. Interestingly, though, in the middle panel, the effect on the heartbeat rate is apparent long before you start to see overt toxicity. And we feel this is important because the patients that suffered from this suffered from cardiac beat problems and not necessarily cardiac cell death. And we've done a series of other drugs, some of which I can't pronounce, so I'm not going to try. But my colleague, Alex Skardal, that did a lot of these experiments, has gone through a panel of drugs and has shown toxicity sometimes in the range of dosages that you would expect in patients that responded poorly to these drugs. Sometimes the organoids are more sensitive, sometimes they're more resilient, but we do see effects. And he's screened a panel of 12 drugs with a variety of results. And we're playing a lot of catch up now. This was funded off of a government contract, and they gave us a very aggressive R&D schedule, but we're off contract now, and we're going back to try to do some characterization in terms of what do these experiments mean? How do you start to relate PK/PD in a human or an animal to something in a plastic chip? We've got some questions we're working on now. Here's some environmental toxins. These are heavy metals and also the active ingredient in the herbicide Roundup that we looked at. Here's in liver organoids, we see a dose response in toxicity to these compounds. Cardiac, similar. We see a dose response with increasing concentration of the compounds. Now I'm going to transition to some of the experiments we did in the integrated systems. The blood-brain barrier that Colin described, I'm calling this an integrated system because even though it's one organoid, the neuronal component is in the core, and the entire periphery is an endothelium with all the characteristics of a brain microvasculature in terms of the exclusion of very low molecular weight compounds and the formation of tight junctions and the proteins that you'd expect in an intact blood-brain barrier. Colin showed you this picture. Here's the experiment I wanted to show you, and I'm running the same problem as Colin. It's looking awful small, so I'll just make it up, I guess. On the top, there's a series of controls on the left. The third bar over is toxicity with mercury with an organoid that has an intact blood-brain barrier on the surface, and you see no toxicity. The farthest right is an experiment we did the farthest right is with no blood-brain barrier. The one next to it on the left is where we have an intact blood-brain barrier. So with the intact blood-brain barrier, we get no toxicity just as in the controls. Without the blood-brain barrier, mercury gets inside, kills neurons, and we could record that. The bottom two figures are a prodrug and an active drug. MPTP in the left is a prodrug that is not toxic to neurons and crosses the blood-brain barrier just fine. It's metabolized by astrocytes, which is associated with our blood-brain barrier. The way we make the blood-brain barrier is we mix astrocytes, parasites, and endothelial cells, coat that on the surface of the organoids. The astrocytes and the astrocytes and the parasites condition the endothelial cells to form those nice tight junctions. The astrocytes will convert the MPTP to MPP+, which is neurotoxic. But MPP+ does not cross the blood-brain barrier. It can't get through. So what we're looking at here, and just concentrate, the left two bars are controls, just concentrate at the right two bars. So for the, and I need to see this in order to be able to explain it. For this bar here, we have an intact blood-brain barrier, and when we add the MPTP, it crosses the blood-brain barrier, is activated to its toxic form by the astrocytes in the blood-brain barrier, and you get cell death. Without a blood-brain barrier, no astrocytes there, the compound can likely get in because there's no blood-brain barrier, but there are no astrocytes to activate it, so you don't see any cell death. Now here, when we add the activated form of the drug, which can't cross the blood-brain barrier, we have an intact blood-brain barrier in this bar here. The MPP+ can't get through, so you don't see any neuronal cell death. In the absence of the blood-brain barrier, it zips right through and it exerts neurotoxicity the way you'd expect the active drug to do. So sorry about that. Let's see. Just a couple more integrated experiments. This is, all these contain liver. This is an experiment with liver and cardiac. So we use the drugs epinephrine and propranolol. Epinephrine will increase the frequency of the heart rate or the heartbeat rate. Propranolol is a beta blocker. It will block the effects of the epinephrine. So you can see our baseline beating in the top graph there. When we add epinephrine, bang, 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 it speeds up and starts beating harder. When we pre-treat with propranolol, you can see in the third one down, it's the propranolol slows down and diminishes the responsiveness to the epinephrine. When we open up a circuit to the liver organoid, the liver immediately begins to metabolize that propranolol, and you can see in the bottom we recover the we recover the effect of the epinephrine. So it's a simple experiment, but it is working kind of the way it would in an animal. If you treated an animal with a beta blocker and epinephrine, you'd get less of a response. The liver would metabolize that propranolol, and you'd recover responsiveness to the epinephrine. We did some metabolomics to make sure we were metabolizing the propranolol the way we thought we were. Here's a 3-organoid system. We've got liver, cardiac, and lung. So basically what we're trying to do in this experiment is we're going to add bleomycin. Bleomycin induces inflammation in the lung. It's a known producer of inflammation in the lung. And when we ran this experiment, we got IL-8 production from the lung, but unexpectedly the cardiac organoids stopped beating. And we couldn't figure out why. When we added bleomycin directly to the cardiac organoid, it didn't stop beating. So something was going on that was an interaction between these organoids. So we showed that the bleomycin treatment of the lung produced IL-8 as we'd expected. It also, we got high levels of IL-1 beta produced from the lung organoid. And when we started looking in the literature, there were a lot of papers out there saying that high levels of IL-1 beta can have a negative effect on cardiac activity. So we ordered some IL-1 beta, added it directly to the cardiac organoid, and sure enough, it stopped beating too. So what this is showing is that when you add bleomycin, it damages the lung organoid. The lung responds by producing a series of cytokines. And one of those cytokines, the IL-1 beta, is going to the liver and having a negative effect, or going to the heart and having a negative effect on the heart. So these are the types of studies that get us excited because we weren't expecting to see this. It's a response you could only see in an integrated system, and I think it shows the potential of these integrated organoid systems to pick up unexpected toxicities or effects that you would totally miss in a single cell type or even a single organoid culture. There's one of our chips up top that's a 6 microreactor chip. This is an experiment we did with liver, heart, lung, testes, brain, and basically what we did was we conditioned 2 organoid systems, both with liver in them, and after a couple of weeks or after a week, we took the liver module, or we took one of the liver constructs offline, left it in another setup, and then we added capecitabine, which is a precursor to 5-FU. It's a cancer chemotherapeutic agent that's known to have some side effect toxicity in some tissues. So you can see at the top where we have the liver that's able to metabolize the capecitabine to 5-FU, you see cardiac and lung toxicity is expected. When you don't have the liver module there, you don't see any cardiac or lung toxicity because there's no tissue that's able to activate that capecitabine to the toxic form of the drug. And here's a similar experiment we did with cyclophosphamide. Cyclophosphamide is a prodrug that's metabolized in the liver to a toxic form. Same setup, 7 days after we had equilibrated the systems, we removed the liver from one of them, and you can see along the top panel you get some toxicity across the downstream organoids, where in the bottom you don't. So it's another example of how you can use an integrated platform to model the effects of drugs and get results similar or beginning to become similar to what you'd expect to see in an intact organism. And just to acknowledge everybody on the team there at WFirm, actually a lot more people contributed to it than this. And as Colin said, we had partners with a couple other institutes, but the majority of this work was done at WFirm. And we function as a pretty good team at WFirm, so there's a lot of people in that picture that aren't mentioned there that did contribute to this. Thank you very much.
So our final speaker is Dr. Paolo De Copi, who is the professor of pediatric surgery at the University College London. And we'll have a brief panel discussion followed by Dr. De Copi's talk, so I encourage the audience to be thinking of questions.
Good afternoon. Thank you for the invitation and the chance to share some of the data we've been working in the laboratory for the past few years. And again, in keeping with Colin and Tom speak, I will try to make the point about the organoids culture, but more, I suppose, from the clinical point of view. I'm a surgeon. What I'm interested in is to prepare tissue that can be transplanted. And of course, we all know about the limit of organ transplantation and about the fact that really only 10% of the organs that are needed are available at the moment. And that's, of course, limit what we can offer to patient at this stage. And of course, we all are trying to trigger the possibility of engineered biological substitution that eventually can be transplanted and overcome the limit of the organ transplantation. I want to share with you the experience that we had a few years ago now. Will be 8 years from this transplant now in March with Kieran, with his mom here. Kieran was admitted at Great Ormond Street Hospital as a neonate with a defect on his windpipe. So his trachea was stenotic from top to bottom. And we had initially done a opening of that trachea with a pericardium patch when it was just 6 days old and was on ECMO. And that subsequently, of course, we had to use stent. Those stents had eroded, more operation. To make a long story short, in 2010, we were faced with no other conventional treatment that we could offer with Kiran, and we were left with the possibility only to transplant an engineered organ. So just to make this long story short, at that time what we did was to take a cadaveric organ and deserialize this organ and transplant it then with cells that were derived from the bone marrow and from the epithelium of Kiran. As I told you, now it's 8 years from the transplant. He's an adult now because he's 20. I could show you a lot of physiology, but just a couple of data just to show you that the trachea took a good long time, about 6 months to regenerate. But then he allowed him to have really a normal life and to enjoy his life with no immunosuppression and never had a tracheostomy. So he was extubated from the transplant at 48 hours and really subsequently needed 2 stents, but then he's coming once a year for transplantation. His trachea has developed a normal ciliated epithelium, which is functioning. And what is important also for some of the audience at this meeting is the costing. We were talking about a different session about costing on this technology. And while the cost of the transplantation here with grant money was about £250,000, in the subsequent year, the costing was extremely reduced for his care, which was a big advantage for the NHS system. And the trachea, while it shrank in the middle part of the trachea, then maintain a good volume that allow him to have a normal respiratory function. But we know that this is not a perfect solution, and in the years to come, it's possible that this trachea will need more intervention. With these type of organs, what we are trying to do is to engineer tissue using cadaveric organ. And we've just reviewed the experience around the world for the Lancet. Actually, while there are examples that, of course, we don't want to follow, like no proper consent for patient or not proper animal studies, there are other examples like the corneal regeneration of Dr. De Luca, who led also the team that recently transplanted skin for the patient with EB, show that it's possible actually to deliver product that would be beneficial to patient. So our approach involves the gut, and I'm going to show you here some of the experiments that look at the organoids culture. And what we have taken as our experience was, can we use actually our expertise on the deserialized tissue to grow those organoids? For clinical transplantation, one of the main limitations at the moment is the use of matrigel, for example, for expansion of those organoids. And this is a limitation because it cannot be used for clinical translation. So we thought to use other type of tissue and focusing our expertise really on finding a way to culture those organoids. So you see here a gut from a rat that get deserialized in a very easy protocol, easy to reproduce and done by many other groups. And this allow us to preserve the structure of the intestine. So, for example, something that we are doing that we'll present it on Friday now is to try to recellularize this intestine, particularly with very powerful endothelial cells in collaboration with Dr. Rafi at Cornell University, to try to recreate that environment where we could see the organoids. But for this work I will present today, I will focus on the fact of deriving tissue for culturing organoids. So we can scale it up, and we can do with human intestine. This is a child with Hirschsprung disease, where we have taken out the colon. We can destructurize this colon very efficiently and maintain all the structure that you see here. For example, the cryptide structure that is still all well maintained, but there's no cells present. We think that we are doing something new. You just go around the corner of the British Museum and you see that these were done 20,000 years ago, and as a researcher, it's quite depressing. But then we did something else. We thought, people study material, a new composition of stuff for making bridges or making new table using electron accelerator. So with the cyclotron in Grenoble in France, we went there with our piece of tissue. The physics were not looking at us very amazed. And we got a lot of information that we could use eventually to build tissue. So they gave us a lot of numbers, but most importantly, they gave us some visual information that actually resemble what really is a destructurized intestine if you cut them in pieces and you do some histology. So with 3D mathematical modeling, we could actually reconstitute this intestine, and with the idea at the end to use this as a model to print out. So in parallel to that type of imaging, we took the destructurized intestine, and this pig intestine. We lyophilus this piece of intestine, we mince that, and then we prepare with pepsin some gels derived from this intestine. We can neutralize or make it viable for the cells to be seeded, and then of course sterilization is very important. Quite surprising at the scanning electron microscopy, these gels derived from these tissues are very homogeneous, and you see collagen fibers, but the structure is very homogeneous even in electron microscopy. We can see preservation of collagen, GAG, and elastin present on these gels. And then most interesting is the fact that we could actually use this gel for testing, for example, neoangiogenesis. This is a CAM model in a chicken embryo, and we could see that actually those gels have a similar angiogenic properties than matrigel, which is known to have quite a good angiogenic property. So then we culture in parallel mouse intestinal organoids on ECM gel and matrigel, and we saw no differences for the mouse organoids. Here some human organoids also, expansion on ECM and matrigel. And again, we could see that our ECM gel could, at least here in short time, could replicate the results that are optimized in matrigel. But actually, we use those gel that we produce to try to 3D print these gels. So with stereolithography, we printed out this gel derived from destructurized tissue to make a structure that, of course, is very different from what Mother Nature has done, but you can see the villi structure and the crypt structure there present. This is quite interesting because actually I think beside giving the possibility of building tissue for transplantation, this gives a powerful tool for studying, for example, the disposition of the cells and how the cells behave in the villi structure. So we could see the organoid cells in this villi, and we could see that if the dimension were assembling a normal villi structure in the human, we could see that the cells dispose themselves occupying the whole wall of the villi. But for example, if simply we increase that measurement of the villi structure, we did not have cells disposing themselves in the wall of the villi anymore, which is quite interesting as an observation and could offer opportunities to test this mechanism of disease, for example. But quite interestingly, actually, what we have seen that this gel derived from the intestine could offer opportunity to expand also some other endodermal-derived organs, like here is fetal pancreas that is being expanded using this gel. And you can see on the data here showing parallel with Matrigel and ECM Gel that we could see very similar results. This is quite remarkable because who has experience on organoids expansion, the gels that are out there do not actually have similarities to Matrigel in terms of if you compare the two number by number, you see a huge difference within the efficiency of Matrigel and other gel types. And that's why people have still continuing using Matrigel even if there's a limitation for clinical translation. Maybe xenogeneic matrices could be used for transplantation, and we have shown before that using xenogeneic matrices do not trigger an immunoreaction. And of course, regenerative medicine is a clinical reality that we need different tools to implement what we are already doing. I couldn't be be here presenting if it was not the all people that have collaborated to the results I presented and acknowledge the funding which have supported the work. Thank you very much.
So we will open this up to the audience for questions at this point. Sure.
For the first two speakers, endothelial cell function mostly if they have a lumen, and the function of blood-brain barrier is at the capillary level. What you're showing is a round endothelium that doesn't mimic the real capillaries on endothelial cells that are surrounded by pericyte and fractons of astrocyte. How that mimics a real biology? Have you looked at your liver organoids? Do you see luminized endothelium penetrating the organoids? And the blood-brain barrier is a feature of shear stress. If you don't have a lumen without shear stress, it's very difficult to say whether you have leakiness or not, because that gives functionality to the lumen formation in the brain.
Want me to take it?
Not for the brain, no.
For the liver.
Or any of your organoids, do they have a lumen?
Yeah, there's a couple of things. First of all, with the sort of gravity settling, coming together, spherical organoid formation, one thing that we always see, whether we do it with liver or brain or whatever, the endothelial cells always partition to the outside. And we don't know whether that is a phenomenon of the density of the cells, if they're just coming in last and forming that external shell, or whether they're actively looking for a tissue fluid interface as they would in the body. You're correct as far as the geometry goes. That's not how capillary systems are arranged geometrically, but it is a single cell, a single endothelial cell that's separating the fluid phase from the tissue phase. Goodwell Newell, who's the graduate student that's been working on that, he is currently trying to do exactly what you want to do, because he's interested in being able to recreate that physiologically relevant shear to get even better function out of the endothelial cells. So what he's doing now is he's trying to create channels through the tissue organoid where it would feed it from the inside out and try to reproduce those experiments. The one thing that I can tell you, though, is the blood-brain barrier models that I'm familiar with from the literature, from people like Wixwo et al., and they're a planar construct that they just show exclusion across a barrier, much like we did with our vascular tissue construct. And they've run that same experiment with the MPTP and the MPP plus, and they show a statistically significant difference. But I've never seen one where you didn't. I've never seen anyone do that experiment where you didn't get any toxicity. Where you didn't get any toxicity with the activated form of the drug with the blood-brain barrier. So the results of that experiment in comparison to the other experiments that I'm familiar with are pretty good. So yeah, there's differences. It could be better. We're working on different designs, but I was encouraged and excited by those results. So we'll see where it goes from there.
But one way you see the toxicity, endothelial cells produce a lot of growth factors, endocrine factors like epiregulin, neuroregulin, BDNF, NGF. So if you kill the endothelium, they don't produce these growth factors, and that results in neuronal dropout. So the interpretation can be different from when the blood-brain barrier is affected physiologically, resulting in the drug penetration. That's two different interpretations that if you don't have an authentic tube
Right.
vessel, the toxicity you see is because of the endothelial toxicity leading to paracrine defect on neuronal formation, rather than a true junctional defect. And Christopher Beschholz has shown in 2 Nature papers, growth factor produced by pericyte instruct claudin 5 tight junction formation between endothelium. So you need a crosstalk between 2 cell types for those to form. So I guess this sphere endothelium mimics some of the properties, but not completely.
So I'm curious though if at the cross section of endothelium, parasite or parasite astrocyte and neurons below that, if you take that cross section inside of a tube and just a plug and a cross section on the spheroid that's coated, the interaction seems to be the same between those. With the tube, what you can get is that good shear, so you get the actin fiber alignment with and the more robust structure. So I don't know, in terms of your the drug causing release of cytokines that could affect the blood-brain barrier, how using our model, is there a way you can think of that we could validate
Yes.
that our...
So the endothelium you use here is brain endothelium or is it generic endothelium here?
It's brain microvascular endothelium. It's primary brain microvascular endothelial cells purchased from a vendor, and it's mixed with parasites and astrocytes.
So those are the immortalized commercial ones. It's not immortal.
No, they're primary, not immortalized.
Because there are many papers published. As soon as you take brain endothelium, you put it in culture, serum hits it, all the transporters that they claim is in brain, it goes away. You can check it yourself. So all these commercial sources are not up to par of physiological.
I know Goodwill has struggled with vendor sourcing and lot-to-lot variability in the performance of them. The MDA and glucose transporters are intact in that structure that I showed you.
Yeah, I have a follow-up to that and then an unrelated question. So to me, and I think kind of expanding on what you said, I think what you're modeling, the lumen would be on the outside of the spheroid, because when you show...
It's an inside-out.
Yeah.
It's an inside-out vasculature.
So my question is, with the blood-brain barrier, you have the astrocyte end feet on the CNS side of the endothelial cells. So if you stain with aquaporin 4, something that would stain those astrocyte end feet, do you see them kind of encasing the surface?
Yeah, and in fact, I think one of the images that Colin showed exactly that. It was confocal microscopy showing that the endothelium, he had markers for endothelium, astrocytes, and parasites, and they all co-localized to the surface of the spheroid. If you meet with me afterwards, I'd like to give you the contact information for the graduate student that's working on this, because he'd really value any input that he could get in terms of advancing this model.
Yeah, my second question, as an immunologist, I'm really interested in cells, like antigen-presenting cells and T cells, leaving tissue through lymphatic vessels, going to the lymph nodes, and then trafficking back to the tissues through the blood. So in the future, I don't know, maybe this is being worked on now. Do you see that system? Like, is
So here's where we're at with the immune system. And there's if you've seen any of the latest, NCAT's calls for proposals, the funding agencies are really starting to want to see an attempt to integrate an immune system into tissue organoid constructs. We include macrophages in our systems. So when you've got macrophages and fibroblasts in your tissue organoids, you can get a TNF-alpha response in following some sort of insult. We can't model anything that's an MHC restricted event. We're working on with the lung, and you can see there was what's the group up in Boston that does the lung where they add the bacteria, and you can see the monocytes and neutrophils from the fluid phase in an air fluid interface lung model. You can see them infiltrating into the lung tissue after you add bacteria to the lung. So you can get for monocytes and neutrophils anyway, you can model infiltration towards an area of inflammation in a tissue organoid. John Jackson, actually, who's in the audience, he's working on modeling thymus organoids, where you can support maturation of immature thymocytes to a mature T cell phenotype. And you can envision in the future someday, if IPS technology gets to the point where we're able to differentiate all the cell types that we need to build tissue organoids and add an immune system, then you could start to model immune phenomena and events, even ones that involve MHC interactions. So we're doing the best we can with the technology we have now, but I think that if we have this conversation in 10 years, we're going to be talking about some fairly advanced immunology on chip.
So has anyone cultured lymph node cells with the tissue and
I think there is a model of B cell maturation out there, and that particular model actually will produce antibodies. Another way of thinking, I think you're absolutely right. Any body on a chip's not complete without an immune system. There are basic bodies on a chip that have been made completely from IPS cells, but even then you've got a problem, because then where do you get your immune system from? You can't make an immune system from IPS cells, not a complete one. So another way that I was thinking of looking at it was to make an IPS line from a known individual, maybe make a couple of basic organoids, like maybe say a liver and a heart, because it's very, very easy, and then take the cells from that known individual and put those into that organ on a chip. Then you've got a full variety. You could then think about perhaps making that liver into a cancer, and then seeing how the immune system would react in that body on a chip to cancers, and how CAR T cells that you would make. But that's all on paper. I'm sure it will be. It's got to go that way. Otherwise, the immune system is so central to the body. It has to be. If you're ever going to think of this as a body on a chip, it has to have an immune system.
A really impressive array of tools with levels of analysis. I'm kind of thinking about with this work, this is really brave new world stuff, but have you started to think about how you're going to meet the challenge of coming up with metrics to assess the standardization and reproducibility of this practice?
So
we've certainly thought about it.
reproducibility, at least for our system, reproducibility is not our long suit. You can imagine why that might, also be a benefit if we could get a series of systems set up that represented like different liver metabolic phenotypes. You could screen drugs for people that are like rapid acetylators, or have different different phenotypes as far as handling drugs go. In terms of how do we start to assign numbers? And the DoD and the government are interested in this. We developed this with the Defense Threat Reduction Agency, and they'd like to use it to screen biochemical warfare agents, model the effects of biochemical warfare agents, and look for development of countermeasures to those biochemical warfare agents. And one thing they're talking to us about is, well, if you make 20 of these things from 20 different cell sources, what criteria are you going to use to determine which ones are, similar enough to the last ones that we can start to compare data among them? And one thing that we don't have, I mentioned before that we had a very aggressive R&D schedule. I mean, step number one when I read the contract was keep primary hepatocytes alive for a month in culture. Right, and when I looked at that, I got a good liver background. I was like, well, that's kind of a non-starter there. Once we developed this strategy for including all the cell types and get these compact structures, they seem to be, very, very self-supportive. But in terms of how we're going to look at these things, and are they functioning normally? Are they functioning the way the last ones did? We're going to have to bring in some hardcore pharmacologists that understand pharmacodynamics and kinetics at a level beyond what we have access to right now at the institute. And more importantly, how do these things translate from an animal or a human being to a model system on a chip? When you're thinking about protein binding and bound drug versus free drug and biodistribution and biopartitioning and things like that, when you're moving through a combination of synthetic and biologic material, how do you start to apply some of the principles that we've got pretty well worked out in an intact organism? How do you start to apply those to a series of tissues on chip? And I think that's when you'll start to come up with some ideas as far as how to characterize and how to validate system to system.
If I could just add a little bit to that. There are companies out there right now. One of them's in Sphero, and Organova, I suppose. But certainly in Sphero, they offer single organ liver screening, and they have a very, very defined process for making them extreme. I know that because my grad student works there, or did work there. And they have been rather successful in attracting pharma companies for screening their drugs. Their main push is quality. The organoids are all exactly the same. They are all exactly made correctly. They are, and all the toxicology in the world's been done on them. I think where we are going, is one step further. One liver's, it's better than a monolayer, but it's not there where we are going. We want to make a body on a chip, and that's a whole log order different from just having a liver, and that's where, of course, all the problems will come. Hopefully, we have a program right now in which we are not only printing the organs into a chip, but printing the whole chip itself. out of a single material. So that, we'll print all the microchannels and all that and dump all the cells and organoids all at the same time, which will then lend itself to high throughput manufacturing of these. The Army are pushing us, and this is totally crazy. They want a dried down body on a chip that they can reconstitute at any time, and the soldier would put in his backpack.
They want to be able to add a drop of water in it.
Yeah, exactly. And believe it or not, there are people working on that and drying cells down somehow. I don't know how, but they are working on it. So who knows, never say never. Maybe in 5 or 10 years, that's what you'll have, a little microscope slide with 25 organoids on it with a immune system all dried down, and you just add a drop of fluid and you're off. Who knows?
Dr. Rafi.
Question from Paulo. Your ECM is very exciting. If you get the intestinal ECM, does it work for heart, or they're all, you think, specialized type of ECM?
Thank you, Shannon. So far, we have only tested with endodermal-derived organs. So we've tested with pancreas, we've tested with liver, and with the intestine. We haven't tested beyond that. It's possible that the ECM will contain some specific factors that will define at least origin. And so I would put my money on using different ECM for at least a group of organs rather than one organ that becomes difficult to translate. Yeah. Thank you.
I'll add, I think, John, didn't we do an experiment with your thymus model where we tried using liver extracellular matrix in place of the thymus extracellular matrix, and we got good results with liver on the thymocytes, didn't we? That being said, I did some experiments where I decellularized normal liver and a partially hepatectomized liver that was regenerating, and a partially hepatectomized liver where we inhibited mature hepatocyte proliferation and forced stem cell mediated regeneration of the liver. I decellularized all three of those, and then took that decellularized material, equilibrated it in rat serum, and then washed, and then solubilized, and then did growth factor analysis on each of those, and we got wildly different growth factor profiles based on the proliferation state of that liver, which was telling me that for normal liver versus each of those distinct types of regeneration, there's probably a provisional matrix that's built during that regeneration that is binding growth factors that are supporting that physiologic event. So there are differences between different matrices in terms of growth factor binding. So we'll probably run into situations where this matrix is optimal for these supporting these cells and these phenotypes.
And if I may, to Colin and Tom, I mean, your system is very powerful. Have you ever tried to use primary derived cells rather than commercial one to use it to make organoids from primary cells?
All the cells in our system are except for for the cardiomyocytes, because adult cardiomyocytes won't beat spontaneously.
Yeah.
And a couple of the cells in the testes, I believe. But they're all derived from cadaveric tissue, primary isolates. I mean, we could probably isolate them ourselves, but two things. One, the contract that we developed a lot of this off of insisted that we use commercial sources because they wanted other groups to be able to reproduce it. And second of all, there are companies that have gotten very good at isolating hepatocytes with high function, pancreatic cells, whatever you need. So why reinvent the wheel? And it's cheaper just to buy it from them.
We'd need another bunch of technicians to do that. But the testes, that's we do that ourselves. Those cells you cannot buy, and we've made I think about 8 different we've made spermatogonial stem cells and also kept the Leydig and Sertoli cells from about, I think about 8 different patients, including one prepubertal boy, which is rather interesting. And we've got a lot of material because we cut the testes into tiny little 2 or 3 millimeter pieces, keep them frozen in liquid nitrogen. And after 6 or 7 months, we usually throw the stem cell culture away and just start again. It's relatively easy.
I think part of the answer to the question about reproducibility and standardization, firstly, will mean it's what you're going to use it for that's going to dictate what the answer to that question is. But I think Paolo's point is also an excellent one, that for certain uses, when you run an assay and it comes up with an answer, then rerunning it with primary cells that you know should be equivalent to what you think you've developed in the dish is a very sensible control experiment to do.
Well, all our cells are primary cells. It's just we don't isolate them ourselves. None of them are from IPS apart from the cardiomyocytes.
They're all derived from cadaveric tissue. All the cells.
All of them.
And so, like, and here's another good example. When, Colin screened primary hepatocytes from a range of donors, he selected some that worked well in our experiments. We reserved that lot of cells and used them. But we did so many experiments, we eventually depleted that lot. So then we went back and he ordered some other cells from some other companies, and experiments weren't working the way they were before, and he had to go through and screen a bunch of other donors. Now those ones that didn't work as well are those, what is the viability was good. What is it that makes the cells from one donor work in our system and not another? That's another thing we're going to have to get to the bottom of if we're going to, because it could be we're selecting a cell population that's going to give us an oddball answer because it seems to be the outlier cell lot that is giving us our results. So
I've been learning a lot about bulk and not about humanity.
Exactly.
That's why I personally like the idea of deriving everything from iPS cells. But of course, the iPS cells that you get are not particularly mature. Certainly the hepatocytes aren't. But if it came to the point where you could derive at least the basic cell types, and then you could grow unlimited amount and always have the same.
And with the liver, the endothelial cells, the fibroblasts, the Kupffer cells, lots of times they're from different patients.
Well, they are. I mean, yeah.
But the problem with iPS cells or pluripotent stem cells, they don't mature beyond fetal stage.
That's right.
And you just heard from Japan that the pigmented epithelium being injected in one patient could be the scaffold defect, but they had to take it out, probably went back again, and that caused inflammation.
Right.
So I think you have to be careful with iPS or even pluripotent. You don't know how to push it all the way to maturity.
Oh, absolutely, yeah. I'm saying it.
The oncogenesis, there is also epigenetic prints that you have to be very straight.
Absolutely. I was just saying it's a pity that we can't use the iPS cells. I wouldn't even think of using them for the clinic, but we are using our body on a chip as a testing system.
But the whole field of direct reprogramming is getting a lot of momentum, so you can get one patient and rather than going to reporting and directly reprogram
Correct.
parasite
Yeah.
And it's also possible that, and we've been talking about doing these experiments in the integrated platform that can have 24 different cell types in it that are conditioning that media. Maybe there'll be factors that are produced in that push those iPS cells a little farther down their differentiation pathway and hold them there. So we'll see what happens.
All right. Thank you to all our speakers today for this exciting session, and thank you all for being here. So appreciate it.
Thank you.
Thank you.